Thanks so much for having me here. I don't know why I'm here. I've done a fair bit of using AI together with neuroscience, but recently I worried a lot about causality, and therefore I will just blatantly use my spot here to tell you about causality and why I'm worried about it. So, got a remote clicker here. Let me talk about why most claims to causality are bogus and how to sometimes get it nonetheless. And I should say the last talk perfectly set me up for this, because in the last talk we talked about weights and what we should do with it, and where do weights come from? Well, maybe we'll have next generation connectomics that directly reads out the weights for us. But until that happens, we're trying to use electrophysiology to get at weights, and I will try and argue in my talk that this will not get us very far. So first, let me motivate why I'm even talking about causality. Why am I a neuroscientist? Well, there you see my brain from a long time ago. That's one of the very few images I have from my PhD thesis, MRI on Konrad's brain. Clearly, I'm partly a neuroscientist because I want to cure diseases. Like we all have in our families, people have had brain diseases and who really suffer from it. And then the main driver for, at least for me, now everyone is somewhere on that continuum, how much you care about those two deliverables. About neuroscience, we want to understand brains. And with the idea that ultimately maybe we can understand something about ourselves in the process. So when we do that, what do we usually mean with understand? Well, if I asked you, what do you mean with understand the brain? You'll be like, yeah, somehow I want to know how the neurons in your brain, when I show you my hand, enable you to say there's a hand. And what does it mean for some highly important people to decide what it means to do neuroscience, or at least fundable neuroscience? I want to read from the NIH's NANDS division of neuroscience. They support extramural research, yeah, that's what they do, aimed at understanding fundamental mechanisms of development. Structure and function of the nervous system in health and disease is about mechanisms. NSF, the Cognitive Neuroscience Program, seeks highly innovative proposals aimed at advancing a rigorous understanding of the neural mechanisms of human cognition. So it seems that at least the funders are pretty much in agreement that everything is about mechanism. And I will tell you in my talk that mechanism is really difficult. What is mechanism? There's a wonderful paper, recent paper by Ross and Bassett. I recommend all of you look at it. But you can say for something to be a mechanism, we need a causal chain from A to B. And we want to know that that neuron makes you see the hand. So that's the causal chain, and an understanding of the chain that gives rise to it. Maybe how that neuron affects another neuron, affects the third neuron, which ultimately makes my mouth say, that's a hand. And this is arguably the foundational definition of causality. The best definition that I ever saw is this XKCD. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. The reason why I love that so much is because it thematizes the one problem with causality. Now the person understands it. Before they didn't. There was a cause in between. But how can they be sure it was the cause? It could have been something else. Maybe the discussions with their friends. And this is the fundamental problem that we have in that space. So let's first start with how correlation and causation are different. You heard my favorite ice cream is affogato. My favorite drink is espresso. Let's look at this coffee machine of mine. This is what I make very nice lattes at my office. If anyone ever comes visit me, I will make you one. It has arguably two variables. It has X, the reading of the pressure gauge. It's no, I want this one. And there is a pressure gauge. Pressure in the machine. There are two mathematical entities here. We have P of y given x, the probability distribution of the pressure in the machine, given the readings and the pressure gauge. And the reading on that thing is going to be really good at telling me about what the actual pressure is, unless it's broken, which is not. Works perfectly fine. So P of y given x is basically, one is the reading of the other, not like they're identical. But there's a different notion here, which is P of y given do x, which is what's the probability of the pressure in the machine if I go in and change the gauge to be at some level. Not like it's a piece of glass in front of it. I'm going to hammer it in, going to take a little needle and I move it to the right. Is it going to increase the pressure in the device? No, it's not. So this is just a nice example of P of y given do x being something different of P of y given x. And this is the syntax that like Julia Pearl got all of us very accustomed to. Let's talk about causal identifiability. Now, like, what's a weight? Now, like, a weight is the causal influence of the presynaptic neuron on the postsynaptic neuron. Now, like, and if I slightly generalize weights, but basically the thing that should figure in our models, if we talk about how neurons talk with one another, it's kind of this function of like what the presynaptic neuron does to the postsynaptic neuron, which is the causal influence that it has. There is a very well-developed field on under which circumstances we can do so. For Julia Pearl has a precise theory of when it's identifiable, and brain science is never identifiable, and let's talk about that. Almost never. One of there's two main criteria, there's a few special cases on top of that. The main one is the vector criterion. A vector path from variable x to y is any path from x to y that starts as an arrow pointing, starts with an arrow pointing to x. Well, that's the definition of the vector path. Given an ordered pair variable x, y in a model, a set of confounder variables z satisfies the vector criterion if 1, no confounder variable z is a descendant of x, and 2, all vector paths between x and y are blocked by a set of confounders. Now, this is a criterion of which variable z you would need to measure under which circumstances to make the influence of x on y be identifiable. Let's zoom out a little bit. No, like that's like the mathematical theory. Anyone interested in causality should like absolutely read Julia Pearl. It really like changes the way you think about it. It changed the way I thought about it, although of course we can't assign causality, as I argued before. Reichenbach's principle. Now, like, let's start at the basics here. Now, if x and y are correlated, then either x causes y, or y causes x, or they share a common cause. No? All three of them are always a possibility. And like then you can say, what we want if we want to get at causality is ultimately find ways of getting it. And much of my talk is about giving you an intuition on when you can and when you cannot figure out about it. And so let's look a little bit into it. Why do we even care? Now, like you can say, yes, like our funders make us, but that's kind of a lame reason. Why do we really want to care about causality? Well, life is about causality. Now, what's a good thing morally for me to do in the world? It's something that causally makes the world better. I might be lucky or unlucky, but like the key thing is, at least if I subscribe to utilitarianism, I want to do things that make the world better for me and others in the future. You can also say simulations are about causality. I want to give you a brain simulation that you'd be willing to call a brain simulation. Probably you want it to be causally correct. Now, if I have a simulation where neurons in my simulation interact completely different with those in reality, then it might be great at describing the data, but I won't call it a meaningful simulation. And fixing a brain is ultimately about causality. You know, like in medicine, I'm going to ask, which change could I do to a patient so that they now feel better, like that now the disease is cured. And machine learning is also about causality. Now, like why do we do machine learning? We do machine learning because it allows us to do better decisions. Better decisions means they cause my outcome to be better in the end, or help us make better decisions. Ultimately, all of machine learning is about the causal effects that it engenders. Now, causality is weird. Also, I want to dwell a little on what causality is. So at the quantum end, now, like physics has a weird lack of causality. At the gravity end, once you like zoom out between big things, sure, there's like the light cone, but beyond that, kind of like it's not sparse. Kind of everything produces gravity on anything else as long as it's kind of like within the allowed part of space. And yet for us humans, causality is clearly extremely useful. So I'm arguing that it's a specific property of the human niche. What do I mean with it? In the world in which we reason and in which brains operate, it's about hunter and hunted, food, shelter, switches, coffee. If you think about tools that are built by human beings, now let's look at this one because it's just on the desk here. This tool has exclusively is caused by it being plugged in the wall, and it causes power supply to my phone. Extremely useful. But it has a very, very narrow causal dependency structure, and that is why it's useful. Now, I can reason about these things extremely well because basically I need power, therefore I need a power supply, and the power supply needs to be plugged into a wall. Super sparse. So causality in the human niche is super sparse. Now, like I'm hunting, not like broadly for animals. There's that one animal that I'm hunting for. Or I'm going for lunch. I'm not broadly going lunching. I'm going lunch with my friend. And there's like a one-on-one relationship there. So in the human niche, in the place where we actually live, causal relationships are super sparse. Outside of that, that might not be the case. No? And human society is all about sparse causal structures. We have a network of friends. It's a very, very sparse relative to the network of all people who could be our friends. And in a sparse causal world, reasoning is easy, thinking is easy, because we can plan on these small graphs and traverse them meaningfully and reason about them meaningfully. And we wrongly believe that things are causally sparse when we leave the human niche. Like, as I argued, let's be clear, the reason why we're in such a causal thing is because as humans, we're good at arguing with it. Therefore, we settled the niches on this planet that are such that causal graphs are sparse. And then once we were a society, we redesign everything so that it's causally sparser because it helps us reason about it. And then as soon as we leave this area where causality is actually sparse, maybe in neuroscience. Now in neuroscience, causality is not sparse. A neuron has 10,000 inputs in cortex. If you go for a couple of steps, every neuron can kind of go from one neuron to all others. And so we wrongly believe that as we leave the human niche, that everything is still causally sparse. And that's why a lot of models we built in neuroscience make these assumptions that are probably not justified by reality. And I should say, this is the bane of my existence. Everyone believes in these simplistic sparse models. And when I work with experimentalists, the set of theories they throw my way are usually, oh, this happens because that simple effect. And like, yeah, but like, what about that other thing? Like, yeah, maybe a little bit, but like, it still happens because of this first piece. So where do humans know causality from? I think causality as a field is rather blind to where that really comes from. The way how we know which things cause other things is mostly because someone told us, certainly for me. Then there's a small number of stuff where I just tried something. When I was a kid, I was like randomly kicking things, was maybe like randomly annoying a few people to kind of see how they respond to it. And from that, I then developed a meta model that I now apply to everything. So, and then there's some cases, so I think that someone tells me is most common. Other random stuff is less common, but it still exists a lot. In some cases, I observe you do something, and I'm like, oh, look, that thing, like, makes the light turn on. But that starts to be relatively rare. Most things are really told by us, or we try it. And then almost never happening is causal inference, directed acyclical graph, Julia-Paul style. Like, it's just like, I'm not solving these detective studies, like, okay, because like, I measured this thing and this thing and this thing, that it must have been that this thing causally affected this thing. It's just not the way people think, and I think it's a distraction to think too much about it. Now, let's talk about why causal representations are useful. Now, they may allow us to generalize better because the future is different, but the causal chains in the world stay the same, allow us to learn faster, communicate better, understand other humans because they also think in terms of causal factors, support counterfactual reasoning in the human niche, and therefore machine learning really wants to get there. Let's briefly talk about the cultures of causality. There's a lot of different fields that say we do causal causal inference. There is a field in neuroscience where they're like, give me your MRI data and I give you a graph. There's a group of people like basically read Julia, Paul, and prove theorems. There's people in machine learning who like look at nonlinearities. Sociology, medicine, epidemiology, they all have their own cultures of addressing neuroscience. And now let's dive into like why concretely on the neuro side things are difficult. So this is a tutorial we also used for NeuroMatch Academy, a very simple setting. I set up a dynamical system, X, and that X is xt plus 1 is AX plus Gaussian noise. I apply some nonlinearity, but that really doesn't do anything in this setting. A now arguably is the causal matrix. Now that's how every neuron influences every other neuron. And we initialize it to 0, and we set the largest singular value to be 0.99 because we don't want unstable systems, like all the usual things you do with it. And now you can say, is correlation causation? And to make it clear, what do I mean with correlation here? In this dynamical system, and think of X as a vector of neural activities. If one neuron is active at one point of time and it strongly affects another neuron, then I expect that other neuron to be active at the next point of time. No? And therefore, the time delay 1 correlation should approximate A. Well, and we can check this. Here you see there's 2 ways of how people commonly visualize that. They draw a set of arrows, very popular in certainly the MRI literature. There's a few other communities that use it. Alternatively, you can plot it as a 2D matrix, which I personally find much easier to read. But the key is here, like we have a neuron number 0, which strongly affects neuron 1, and so on and so forth. Small system, and we can look at this. Time delay 1, at the top you have the true connectivity matrix A, time delay 1 correlations below it. Look, those 2 are extremely similar to one another. So correlation is causation, and Konrad can finally stop his talk, because it would be very convenient if correlation was causation, because if correlation was causation, our job as neuroscientists would be just so much dramatically easier. But of course, I wouldn't show it to you if it didn't look like this. So I have the very same system here that I simulate. Now, like the only thing I change is the dimensionality. I now make it very high dimensional. As soon as I go from 6 to 100, they look very, very different. And I can, of course, quantify that, where the 2 of them are very similar as long as I have like 6, 10 neurons. And they're very dissimilar as soon as I have like order 100 neurons for this generative model. Now, this is calm, because when we think about causality, what we usually think about is like small systems, the kind of stuff that fits into Konrad's head. Now, like, I can think about 5 variables that influence one another and can kind of like simulate them a little in my head and get an intuition for that. That is exactly the domain where we wrongly believe that correlation is causation. As soon as the systems get big, correlation and causation often get very, very different from one another. Now, let's make this concrete. Now, like, this is the so-called omitted variable bias equation. It's extremely popular in economics. I've never seen another neuroscientist put it on slides. The idea here is the following. No, like we're going to make everything as simple as possible. Everything is linear here. And the only thing is we don't record all neurons. No one records all neurons unless you're in C elegans. And we believe that there's some variables that we do record, and we believe they're called X, and other variables that we don't record, we call them Z, and there's noise. The economists call noise U. No, and we can then ask, how's our estimator gonna look like? My estimate of beta hat, standard equation coming from linear regression. Okay, and now we can calculate what is the expected value for my estimator. Well, the expected value, first the good news is that it's beta. Now, like it's if we just look at the first term, this is what we want to estimate. Beta are the actual causal influences of X and Y. But then there's the second term. And the second term is a bias induced by the variables that we did not record. And I want you to think about the magnitude of that bias. Now, like, how many variables do we record? At the moment, about 10,000 if you're like world class. If you're MRI, not any better because you're like lower spatiotemporal resolution, and therefore like the variables are just orthogonal to what you're recording with it. So if we write this out, all the variables that we don't record from are going to bias the result that we have. Now, I want you to realize that the number of biasing variables here are all confounders between them, which is all other neurons. Therefore, the number of confounders that we have is massive, whereas the number of causal inferences that we're measuring is tiny. Therefore, these variables that we don't record from will produce massive biases for us. And we should expect that these biases are orders of magnitude larger than the magnitude of the variables that we do record from. So we shouldn't expect that we can get at weights by looking at correlations. Now, some of you will be like, oh yeah, but we use foundation models. Complicated models don't make the logic of this problem go away. Now, sure, if you tell me, yeah, I know that it's very sparse in practice, you're going to get a certain amount of mileage with it. You will usually just lower these numbers here a little bit. It's not going to solve the problems. No, let me tell you another reason why it's problematic. You can say, okay, Konrad, I agree with you today. But the future is different. Like we have Stephenson's law, number of neurons double every 6 years. Just going to hang tight, and eventually we're going to record all neurons in the brain. It turns out, and then we can correct for all the neurons that we will have recorded from all neurons. So here's a problem. If we correct for confounders, our estimates get better. But there's another thing that's called a collider. A collider is, if we want to ask if A influences B, a collider is a variable that is affected by both A and B. If I correct for a confounder, my estimates get better by definition. If I correct for a collider, my estimates get worse. Now, I told you essentially every neuron acts as a confounder for others. The bad thing is that every neuron is also a collider for any set of things. Like if you have two neurons, eventually their signals will converge on some neurons. And there's nothing that tells me which neurons will be confounders versus colliders. Worse, most neurons will simultaneously be colliders and confounders. So there's fundamentally no way of meaningfully correcting for that. Now, I'm of course I'm always much slower than I believe I'd be, which is great because then I really get to concentrate on this question. So I want to now take my consideration for causality back into the space where they matter, which is the questions. Neuroscientists have lots of questions, as they should. Now, and Tinbergen in '63 said in biology, there's 4 types of questions. There's the question about evolution. How did we get here as a species? There's a question about development. How come that Konrad gets on stage here, talks about causality? What happened before in his life? There's the question of goals. Why does Konrad get up and give a talk? And there's the question of mechanism. Maybe how do neurons in Konrad's head make him get up here and give a talk? Important questions. Who are we to say everything must be mechanism? And in fact, Tinbergen clearly said that mechanism is one of the 4 relevant questions. It's just that with most neuroscience techniques, mechanism is essentially impossible. Why? Because we can't establish causality. Why not? Because our perturbations, almost by necessity at the moment, we perturb low-dimensional. Sure, we can inactivate a cell type, but that's a 1D perturbation. But when you recognize my hand, I'll say, hi, Konrad, that's not a low-dimensional thing. That's millions of neurons in your head that ultimately get activated for that. So mechanism is the one thing that we convinced ourselves we must work on, the only thing worth funding. And at the same time, it's the one thing that most of the time we can't deliver on because we can't actually establish causality. And causality is the necessary criterion that we need to argue about mechanism. And I briefly just want to say, it's also kind of interesting that David Ma, coming 20 years after Tinbergen, somehow killed evolution and development. And Pojo much later said, hey, what if we add development, which is learning, back into it? So it's an interesting piece here. Machine learning lies outside of either Ma or Tinbergen by default, which is we just produce great models, predict the spike density, predict the behaviors. And we've seen some of the coolest work in that space here at this conference already. So do advanced data analysis methods help? I want to do this very quickly. And it brings us to that question of what's the right latence. Here's 3 clouds. All these clouds have exactly the same results if you apply PCA. And very clearly, we are good at describing the latence on the left. We're kind of missing the boat on the latence in the middle, and we have no idea what's happening with the latence on the right. Foundation models. Everyone is excited about foundation models. I'm excited about foundation models. They're the best things we have for solving engineering problems. It's the best decoding techniques. It will dramatically lower the amount of data we need if we want to give someone a prosthetic device. I want to cite here Dan Yeomans because he says what almost all my friends believe at this point of time, which is we want to be able to use the model of the digital brain as a neurobiological discovery and diagnostic design platform. Other people put it in different terms. This gives us a digital twin. There's a lot of different words for that idea. Now, it's a misinterpretation of what foundation models do. A foundation model is a model for the data that we have. The data that we have is observational data. Therefore, a foundation model will always just model P of y and x. It's not going to model P of y given do x. But if I make claims about the medical systems, they're fundamentally about causality. I want to know if it helps you to take a drug. I don't want to ask the question, people who take the drug, are they better or worse? Sure, people who take snake oil live longer than people who don't live snake oil stuff. Why? Because they have available extra income that they can waste on snake oil stuff. And therefore they're higher socioeconomic status, which is totally correlated with longevity in America. So basically foundation models can't give you digital twins on which you can try things. And again, just with apologies to Dan Yeomans, he's one of the best people in the field, and I'm a super fan of what he's doing. This was just a random quote from that field. Everyone is saying it, and there's just no basis to it. So imagine you want mechanism. Imagine okay, I want causality. What can you do? Well, if you can perturb causality is pretty easy. Why? Because it trivially satisfies the vector criterion. If I go in and I'm you neuron will be active or you neuron will now not be active, I can set the input and therefore I'm no longer confounded and therefore I can read out what the causal effects are. And that's why I'm trying, I dislike worms as much as the next person. What's the elegance is it's transparent, it has a small number of neurons. One can very feasibly, and Andrew Leifer has shown examples of that, you can very feasibly basically zap every neuron one after the other, and you can also zap lots of groups. With that, maybe we can get at simulation, where we can figure out what's the input-output function of every neuron, put it together, simulate something. The key is we need the actual causal input-output function. We don't need the predictor for the postsynaptic. I could have a perfect one. And for all that we know, there's not even a causal chain. Everything happens in the mind of God, who sets all the neurons. In that case, there would be no causality at all. But yet, all the neural data would look exactly the same way as it is right now. Good. In any case, I get to skip over a lot of things. It's totally cool. Okay, briefly, how could we use machine learning for causal inference? If instead of training on correlational data, I would perturb on causal data, everything would be fine. So the logic of machine learning can be applied to causal inference problems. It's just we shouldn't hope to use machine learning on correlational data and hope to get causal data out of it. What we should at best hope is that we apply it to perturbative data and then we get causality out. And here's a fun way of doing it. In standard supervised learning, we of course know we have known inputs, we have known ground truth outputs, and we get good at mapping from inputs to outputs. Now, where do causal inference algorithms come from? Now, the world of neuroscience is full of algorithms where people are yeah, give me your brain data, I'm going to give you the network of how information flows in it. The way it works is that these guys are brilliant, and they write an algorithm. And ultimately, I take the algorithm that they give me based on their domain knowledge and apply it to my own data set, and it gives me a network. hopefully about causality. But you can say, well, let's apply the basic idea of machine learning to that. Like if I can give you ground truth causal data, I basically give you a lot of, here's the physiological data and ground truth causality. Ground truth causality is no problem. I just perturb it. I can do it in mouse. I can do it in humans. I can do it in C. elegans. We give it the ground truth data, and then we can use the algorithm to like predict what causality is there. Now, of course, the kind of data we'd need from brains don't exist, or certainly didn't exist when we did that. So we need something, and I love the microprocessor. It's like my favorite model system. And here's the way we've set up the problem. I show you the voltage traces as they come out of two neurons, and I'm just asking you, does the neuron 1 causally influence the neuron 2? How do I define it? I just go in, I stimulate it, I see what happens at the output. Okay? Like simple operational definition. What you see at the top, this is a causal pair. Neuron A does influence neuron B. At the bottom, you see a non-causal pair. Neuron A does not actually influence neuron B. Then we use perturbations to define causality. We use honest validation. It's a trick that Susan Athey has popularized. You basically go divide the data into two completely different halves. You detect the causality detector 1, and you then use it to test. Of course, we use a transformer because everyone does, and they are here. Works great. Works also if we add lots of noise. Works also if we train on one game and we test with another game on the microprocessor, and we can use GradCam ideas to figure out which time points actually drive the decision that it's causal or non-causal. What this means, bad thing is requires lots of data, impossible for humans to understand, totally biased in lots of ways. But if we have enough ground truth data, it should make us better than what any one human can develop, because it ultimately, this is the bitter lesson. Like with enough data, it always gets better. Take home message. Neuroscience is deeply argued too deeply about mechanism. I think there's a million great questions, and the fact that people who discover awesome things get like always chided for, isn't this a fishing expedition? And people who do like pretend hypothesis testing make it into top journals as a problem. Ultimately, mechanism is about causality, but causality is super hard, and we really need to struggle with what we do about it. And if we could have causal data at scale, as I showed in the last piece, we could ultimately overcome that. And with this, thank you very much.
Any questions from Kenny first?
I pretty much agree. Causality is really hard. And my question will add to that. So there is an interesting question of, if I asked you why you haven't been stepped on by an elephant, and then you would say, because I'm still alive, and if I have been stepped on by an elephant, I would die. But this reason by counterfactuals, it is pretty reasonable, but it doesn't explain why you haven't been stepped on by an elephant. So that means like for some theory to have explanatory power, it needs something other than like reasoning by the rules or reasoning by the counterfactual rules or any like logical rules. And then you said in order to study causality, we need to stimulate. But then now, if you perturb the trajectory we go about everyday life, like there isn't anything to perturb to study like why we haven't been stepped on by an elephant, right? So I think what's missing here is intentionality, because like we couldn't figure out the mechanism because we are not intentionally avoiding being stepped on by an elephant. So, and we see similar examples in evolution where like some functions evolved out of some like serendipitous byproduct of other things. So yeah, so I guess my question here is, what do you think the role is that is played by intentionality in the study of causality?
Okay, great. I hear two pieces of the question. The first one is, in Judea-Pearl's rung of causality, there's three levels. There's one, modeling correlations. Then there's the modeling causality. What happens if I reach in and do something different? That's the P of y given do x. And then there's the third level, which is kind of like asking these questions, why did x happen? Which usually in Pearl syntax requires you to combine multiple of these do type statements with one another. So that's the first one. But then intentionality, like intentionality when it comes to the human niche or the animal niche, intentionality is absolutely essential. The way we define culpability within law is, of course, in terms of intentionality. Like if you accidentally do something, it's completely different standing than if you want something, and even then in law it's all about causal, about causality. Would it have happened if you hadn't done something like that? So yes, all of that. And intentionality is essential. It's also essential in the way we interpret one another. And like we know that we are agents. So in that sense, I start my life believing, in fact, like babies do that, believing that others have intentionality. And it's one of the things that it's a human superpower that we basically home in on. What are the things that drive others? What they want to do? Like, and this beautiful work by Alison Gopnik and others that like this intentional stance is ubiquitous in human behavior.
Back here. So great talk, Konrad, as always. Two-part question. So the first part is, well, what are the limitations of actually calculating the do operator on what we want to calculate? What's like the ideal there? And then the second part is, what do you think of so all of this was data trained networks, data trained models. What do you think about task trained models or agent based models or artificial life type approaches in trying to understand the causal mechanisms for the emergent behavior that we see in larger scales?
Yeah, so the do operator is not a tool. The do operator is a way for us to write a belief that we have about reality. Like P of x given do y, or P of y given x given do of x is the probability that y would happen if I reached into the world and set x to a certain value. So like this is a completely hypothetical construct. It's not a tool. It's not something I can apply to a data set. But it's a tool that I can apply to a data set and that the world does apply to data sets to ask under which circumstances is it identifiable. And what we know from there is there's a very, very simple rule, back of the envelope rule, which is if there are variables that are confounders between the variables I care about, that I can't record from, in essentially all cases, it becomes unidentifiable. So you have that all these models use unconfoundedness. There's a few models that instead use a strong notion of faithfulness, but they run into their own kind of problems with reality. So basically, so now, and you asked for a whole bunch of other methods. The Pearl results show that no method can. It's not that like Pearl can. It's not like people who use do operators can. It's a hard mathematical proof that it's identifiable. And let me give you the intuition for that. Imagine you have x and y, and you have any aspect of their joint probability distribution. Now, that's the only thing you'll ever measure unless you perturb. They could always, if I allow you for there to be a third variable confounder, then any joint distribution between x and y can be induced by that confounder. So therefore, like you can directly prove that as soon as I have confounders that are unobserved, anything that I observe in the variables that I have may be misleading. So like in that sense, it's not that a method doesn't allow it. It's like no method allows to do it.
Thank you very much for the presentation. So I have a question about what are your takes on maybe using certain AI paradigms for foundation models and later applications, specifically online reinforcement learning, which seems to be deeply causal in the sense that no matter if it's model-free or model-based, it assumes that the actions change the state or the actions change the rewards that the agent receives. And would you suggest maybe for later foundation models to be trained instead of on online repertoires, which are deeply offline, but instead in certain types of embodied tasks, if we assume that what we really care about is causality in the real world, as in the case of like medical applications?
Yeah, let's talk about reinforcement learning. No, like it's amazing how it works, how well it works, in particular this year. The key is that it's deeply causal. Like what we do when we do reinforcement learning is we have probabilistic policies. The noise component of my policy is a perturbation, a de novo perturbation with nothing that directly affects that noise component. And therefore, that can then help us make good estimates of the causal relations in the world. So like reinforcement learning works because it perturbs the world. And now you can say, if we want to do offline things, it's hugely important for me for the data source to communicate to me what was random versus what was part of like the deterministic part of the policy. No, why? Only when I do these random things can I epistemically be sure that they are my effect. Otherwise, anything would be possible.
Sorry, thank you. Nice presentation. I appreciated your description of the causal bit as being one that's, human scale. And I guess relatedly speaking, in the physics world, you care a little bit less about it because the scale is different, I'm assuming. In that vein, if you think about the connection of a mechanism approach and causality, you link them very strongly in saying that neuroscience is perhaps too mechanistic. But if we looked at mechanism as being largely probabilistic, as you would as a physicist, and potentially complex, as you would as a dynamical systems person, why make that connection, that causality, as a human kind of precept that we want something simple, which the world is not simple? Is that link so tightly linked to mechanism? Can't the mechanism just be probabilistic and complex?
Oh yeah, and it could be complex, high-dimensional, all those things. It's just in those cases the mechanism becomes not identifiable. No, like I'm with you. No, like let me be clear. I'm 100% with you that the mechanisms suddenly in human brains are super nonlinear, super high-dimensional, super complex. All those things. It's just then we shouldn't believe that we can identify how those mechanisms work. Unfortunately, that is the business of systems neuroscience. No? Like, so that is what I'm homing in on, that we have that internal disagreement, that we say systems neuroscience means get at mechanism, and at the same time, well, but I can't tell you mechanism because I can't figure out causality.
All right, let's thank the speaker again.